Welcome back to our series of Future Farm Resilience podcasts hosted by NIAB, working in conjunction with AKC and Savills. I'm Will Vaughan-France, your host, and today I'm going to be talking to one of our colleagues within NIAB, David Clark, who is a specialist in precision agriculture and some of the spatial techniques. We're going to have a bit of a chat about data, a bit of a chat about precision farming and how it might help us to actually improve decision making on farms. So welcome, David.
Thank you.
Probably just as a way of kicking off a bit, could you just perhaps give us a run through for listeners of what sort of work you're actually doing, what your PhD is in, and the wider work you're doing within NIAB to give people a bit of an understanding?
Yeah, certainly. I'm David Clark. I'm a soils and farming systems specialist at NIAB, and primarily for NIAB help deliver some of our long-term experiments at Morley. A lot of the work I do is based at Morley in conjunction with the foundation there. But I'm also doing a PhD with Cranfield University with NIAB and the British Geological Survey, and we're looking at how we can manage spatial variation better on farm. I come from a crop modelling background, and we're just looking at whether crop modelling can help us understand spatial variability and actually manage it alongside current precision ag techniques.
So could you just explain a little bit what you mean by crop modelling there as well, just for, because for the audience as being, we're more at the operational side rather than the sort of academic side. So what do you mean by that?
Crop models are a sort of collection of mathematical formulas that they're mechanistic in their function. So they describe how plants grow with their interactions to weather and soil properties. They're not sort of linear regressions. They work on a daily time step. The ones I'm working with sort of model leaf area index, and then they'll take into account any sort of drought or nitrogen interactions with that. So if we can accurately describe a soil through measurements, we can parameterize that within the model. We can use historic weather data sets or even projections and see how the model suggests the plant will grow and interact with our management within that. So, for example, in a precision ag context, we could have 4 or 5 zones across the field that we know to be spatially different. Looking at our yield maps, we could soil sample them and parameterize those soils within the model. We can run nitrogen experiments for 20 years of weather data on those different soils and say this is what the optimal nitrogen rate is historically. Therefore, that soil has a natural limitation, or that soil potentially could yield higher. And then we can adjust our management from that. So this is all a bit sort of in the testing phase. We haven't got that on farm. We're trying to work and getting it onto farm at Morley and seeing how well it does using real farm data, whether that's yield mapping, EC scans, protein sensors. I'm also doing some NIAB work. So we're looking at how EC and soil electric conductivity and yield maps, weather data can help explain spatial variability on farm, but then also validating how current precision ag technologies, whether it's looking at nitrogen or seed rates, interact with that and whether they actually lead us to a better management system.
So a lot of this is quite interesting with spatial. I mean, I was just thinking back that yield maps, I think the first ones go back to the late 80s, sort of 1988, 89 sort of time. I mean, EC scanning's been around for quite a long time. I think that was sort of late 90s, probably with some of that. Some of the variable rate technology, something like the RN sensor, I think would go back to the late 90s. So we're talking about some of these technologies are, actually quite well established.
Yeah.
But there seems to me a sort of challenge that maybe we haven't worked out how to actually get the value from a lot of these systems that we really should. So is that really sort of driving behind a lot of the work that you're doing then, trying to actually turn these from sort of symptom maps telling you what's going on to decision making information?
I think if we look at the first sort of 10, 20 years of precision ag as our data collection phase, one yield map on its own, although interesting, may not be particularly useful because, we had some pigeons come down on that part of the field, or we had some rabbits attack that part of the field. But when we have 5-10 years of wheat data, for example, over different seasons, different weather patterns, we can start to say, well, is that spatial variation consistent? Is it something we can manage consistently? And the things like, you mentioned the EC scanning, you mentioned N testers, and actually those things are really useful. But actually, if we have an EC scan 10 years ago, for example, great, we can see that variation, but is that variation consistently impacting productivity? Well, we need 10 years of yield maps to make that decision. So You're correct. They were interesting and useful early on, but actually over the last 10, 15 years, as farms have started to develop 10 years of yield maps, and we can overlay weather data with that, we can look at how that interacts with soil property map, whether that's EC or whether it's targeted soil samples. We can start to build a much better picture. But also those data sets can help us validate other precision ag technology. So, for example, we may have brought on an end sensor on farm, and using that, we can say, well, look how our yield map has evened up, or look at how we've reduced nitrogen over the last 5 years. So they can help us validate what we're actually doing on farm, and that's only become more recent as those data sets have got larger. Now there are issues with those data sets, as we've done, looking at how accurate they are and how we interpret them, and they're big, and we have to calibrate them, and one's in this piece of software, one's in another. So bringing them together is where a lot of the research has gone on sort of in recently.
You raised something there that actually just sort of flagged straight in my mind, which is you talked about nitrogen rates, and we've entered, and we've maybe evened a crop up. Is that actually desirable, to even a crop up? And the reason I say this is that surely different parts of fields and different zones have different levels of potential, and to even something up is, I mean, the easiest way to even something up is to even it down. So are we actually looking to even things up, or are we looking to actually accelerate the performance and maximize the performance of every area of the field and actually harness variability to our benefit rather than trying to raise it?
I suppose the answer depends on what the cause of that variation is.
Yeah.
I know we're using nitrogen as an example. Nitrogen's nice and easy. One, because we spend quite a lot on nitrogen. From environmental goals, it's important, and it's an easy example where we can make financial, economic, and environmental gain. So it's good one to work with. But the principles apply to most PA technologies. But if your limitation is nitrogen, then obviously those lower areas that may just need more nitrogen, and that nitrogen doesn't impact your nitrogen use efficiency, then great, we've evened the crop up. I get your point that, and it's a limitation of some of these technologies, is that a lot of them that only look at one factor. They may not look at how a specific management technique interacts with, say, soil properties. Our end sensors or our canopy measurements can give us an idea of how the crop is performing without actually going and doing some soil sampling or tissue testing, whatever it might be. We don't actually know why that's doing that. And now if that's something that's irrespective of nitrogen, or irrespective of what we're trying to change, then actually doing that change may not necessarily give us fantastic economic improvements, and actually it might give us environmental issues. Yeah, exactly. So that's not been said, they're not very, very useful tools, but we need to go ground truth what we're recommending and what we're doing, and say, yes, that's definitely the right prescription for that area. It's probably a misconception that pre-A makes life easier. I think actually to really use them, they do need human input, and we need to go and check what they're recommending and say, yes, I'm confident that that recommending is correct for that area. And yes, over a number of seasons, that's definitely generated the response I want and I'm acceptable with. People have different perceptions of risk. They might be happy to reduce nitrogen on that area because it's always under yield performing. But also people might have, actually, I know that's a sandy bank, I'm not happy putting more nitrogen on that area because there's the risk that a lot of that will be leached. So there's those sort of local ground truthing that needs to happen with all of these technologies, whether it's seed rate, whether it's nitrogen, whether it's precision cultivation, whatever you might be doing.
Yeah, I mean, there's a certain amount of precision farming that as a farmer you kind of understand because you actually do already.
Yeah.
Because particularly if you're the operator yourself and decision maker, where maybe you're going to need a bit more fertilizer or a bit less. Where crop will often lodge, and there's a high level of precision farming that many of us actually do without thinking about. And perhaps this is trying to bring it down to perhaps a slightly more thorough, more detailed way of looking at perhaps some of the less visible variation. But then we come into an issue of resolution, don't we, as well? And as equipment's got, so if 36 meter tram lines, 36 meter resolution maybe on sprayers and spreaders, at what point are we in danger of trying to become too precise? Is there a sort of resolution that's ideal to work with, or a practical compromise?
Yeah, I suppose when we talk about precision ag, we tend to think of the sensors, and actually a large part of improving precision ag is actually from the technology, GPS guidance, the benefit that brings, avoiding the spread or spray overlaps. We can precision drill wide row crops. We can precision, into row hoe. So actually those GPS technologies make implementing precision ag a lot easier. So yes, we have a 36-meter boom, but we can do section control and bring that into different areas. Now, back to your original question, it depends on the size of the spatial variant. If you've got big, large zones where you've got a sandy gravel bank, that relatively is easy to manage. You go somewhere in the Brex where you've got these, sand waves through the field at 1-2 meters. Well, actually, that might become a bit harder. And we are sort of limited by the resolution of some of our data. As combine headers get larger, the resolution of our yield maps becomes smaller. So we have actually less information on the spatial variation of yield than if we were using a 6-meter header compared to a 9-meter header. Going back to the yield mapping point of view, you're limited if you're making decisions based off the variation in that, you're limited by the variation and the size of your yield map. But that's always going to be 15-20 meters squared, which is probably the way soil varies is fine enough. And actually for our management decisions is going to be fine enough. And it's only really those areas where we see consistent large variation that these technologies are going to deliver large economic and environmental benefits. So yes, there's a limited resolution, but actually where we've got these big areas is where we want the technology to work and where it should be working. I know, Will, you're a farmer. Your variation across the farm, do you see it as a manageable scale? As in, are you worried that...
I suppose I'm in a slightly different scenario to many in that if I look back at a map of the farm from the late 1800s, I find that very few of the hedge lines have changed in that time, and most of them were there for a reason. So we're operating in fields that average less than 4 hectares.
Right.
The level of it's interesting. How much we get perhaps less variation as a result, because actually we've got hedge lines marking where most of the variation was originally found. So I'm probably not the best person to ask that one. Nonetheless, I mean, things like yield maps are very interesting. NDVI maps are interesting. They show variations. Some of those variations come down to things that are absolutely nothing to do with the soil properties. You've mentioned rabbits already. That's one of the great benefits of having as many hedgerows as we have, aside from the enormous hedge cutting bill each year, is the rabbit population that it suits. But you do sometimes see certainly fine changes in soil, fine change, and often down to how soil deals with very wet periods of weather. And here, I think it's an interesting one with yield mapping and how it's flagging the effect of sort of climate resilience as well, and weather resilience, that flagging wet drought areas, flagging areas that can't cope with excessive rainfall, not always the same areas, but sometimes perhaps maybe that leads me on to something about, well, what is a yield map? And is it fair to describe it really as just a symptom map?
Yes, I think it probably to a level it is on its own. You've just got a measure of the variation. Now, before we go and look at any other technology, most farmers will then be able to put some context to that variation without we go and do any scanning. So it's a symptom map, but then we can also then make informed decisions off that. For example, that you've just described that area is wet and heavy or down the bottom of the slope. You go, well, actually, maybe I could look at the drainage. Is drainage working? Is there something we can do? Can we mold drain it if that's suitable? So yes, it is, but then you can make more informed decisions. Then it's also, I think, yield maps are sort of the end point. They help us see if there's something we could do differently, but then they also help us say, well, what could we do differently when we look at the other technology? So if we had an electrical conductivity map, which in theory might be measuring variation in soil texture, say, across the farm, well, really we're only interested in managing that if it's having an impact on yield. So we can overlay the two and say, look, we know texture's changed here and our yield response has changed here, therefore we could do something different. Now let's add an end sensor to that, and we say, look, our soil map is showing this, our end sensor is suggesting we do this, and our yield map suggesting we might get benefit from that. Well, then we can then use those yield maps in years 2, 3, and 4 to say our change of management has had a positive or negative impact on yield, and we can then go do maybe some targeted sampling of soil to say, yes, it's achieved what we wanted, or targeted grain nitrogen measurements, for example. So yes, it's a prescription map, but really it's I do see them as the sort of the fundamental pillar to most of the other technology was trying to imply. Because what's the point of managing something if it's not actually impacting us economically or environmentally?
Well, yeah, sure. I mean, because why you need to have a motive behind doing something,
Yes.
sure. And for most people, that's going to be that it needs to improve the productivity and the economics of the business or the environmental aspects of the operation. But with a yield map, then maybe what we're saying is actually you need to kind of sort out a lot of the basics first. Because if your yield map is just showing you that some areas are low yielding, and well, that's because it's not drained, or not drained very well, or sitting wet, so or it was a rabbit-eaten headland, because you don't need a yield map maybe to tell you that. So
No.
Perhaps is it actually potentially much more useful when you have a yield map where you've actually dealt with all of the obvious factors already, and so the drainage is good. You've got rid of the obvious problems that you maybe don't need a map to tell you are there, that you sense from walking around a field, and then it's that sort of residual variation, which could still be massive in a field, which you can then start to enable you to start to understand the variation that isn't obvious.
Yes.
Or is related to fixed characteristics that you can do nothing about. Obviously, you can't change a light soil into a heavy. Well, you can, but it involves a lot of lorries to do it.
Yeah, and I suppose it goes down to fundamentals that inherently areas are going to be limited by their certainly soil physical properties. We have that yield variation. We've ruled out the obvious drainage factors. Well, then your targeted soil sample can say, well, is it because of that lower yielding? Phosphate's an easy one. Is that those lower yielding areas, if they've been low yielding for 10 years, actually, if we've done blanket phosphorus applications, well, we might start to have indices 3 and 4. Well, our soil test will say, okay, well, probably if we accept that that's always going to be lower yielding because it droughts out or whatever it might be, maybe we probably don't need to put on our full rate of TSB because it's fundamentally offtake is a lot lower. So we then have some sort of diagnosis and some which isn't necessarily related to yield, but actually could deliver us an economic and an environmental benefit. And then with that soil test, we can look at the texture and say, all right, well, fundamentally, it's a sandy area. Certainly at Morley, we're in the east, 600 mil of rain a year. On some parts of those soils, glacial till, we've got these sand and gravel banks. Every year is a drought year. So we know consistently that part is going to be performing differently to the other part. It varies year to year on the intensity of the rainfall, but we know that actually we maybe want to be doing something different. Now, I'm not necessarily that worried about how we get to what method, whether it's precision ag or soil sampling or targeted grain nutrient sampling allows us to make those decisions. There's very different ways, but we can start to make those informed decisions based on what we know, whether it's nitrogen, whether it's phosphorus, whether it's seed rates, and even just playing around and testing does what if I didn't apply any N, what's our zero nitrogen? What's our back? Is it variation in background N levels, or is it variation in whatever that might be? Till accounts can help us identify differences. So a long answer to a short question, but I think they are symptom maps, but are very much sort of fundamental of identifying what we might want to do different.
So you've obviously got potentially all sorts of trends with actually data quality as well. So if you're somebody who's collecting data in spatial form, and it might not just be yield maps, but it could be all sorts of other maps as well, what do you need to do to make that data valuable and to make it useful? Can you take it at face value?
It depends on how you're using it. If you just want to, identify, again, we're using yield maps because they're an easy example, but it applies to EC, it applies to whatever you might be doing. If you just want to identify variation, then probably not a lot. If we're not that worried about the accuracy, is that actually 10 tons a hectare? Is that actually 7? But the variation is 9 and 12. Well, they'll give us that picture just by printing them out and looking at them, so we can say they've got that variation. Now, if we wanted to do more complex things with that, some work we've done with AHTB at Strategic Farm East is looking at how they can use to identify marginal land. So we want to ascertain a really high accurate economic value to that portion of land. Now, we need to be very, very confident that those yield maps are to a degree of accuracy. Now, we were able to validate over 250 yield maps with grain trailer weigh cell yield data and showed generally they're pretty good, but there is potential for large error. And across sort of 150 wheat yield maps, the error was around about 0.8 tons a hectare, which when you start to think about what we're being paid for some of the environmental schemes is, quite a large, when wheat was £300 a ton a couple of years ago, that's quite a large economic error in the analysis.
It's a large part of the profit as well,
Yes.
particularly,
So,
or not.
so we need to be a bit careful how we use them in that sense. Now, that being said, because we had those grain trailer waste cells, we could apply some sort of correction to it, and a lot of the software that people might use might allow you to do that sort of post-calibrate yield maps based on what you record. And I would encourage people to do that if they want to use them to make those economic decisions. And then from a research point of view, I'm finding that the errors are sort of coming up, causing issues when I'm trying to validate a model. Before we use these models across farm, we need to know that they're accurately representing what's going on within the soil and they can model the yield potential. Now, if we can't measure the yield properly, how am I knowing if which model's performing best at recreating that yield? So they are, the accuracy of them is important to recognize as a limitation and do what we can to improve that. The first thing is certainly just clean the data up, and a lot of the software that is available to farmers, a lot of it's free at use in terms of the point you can pay extras for different things, but you can upload yield maps regardless of what combine you've used to them, and they all do a good job of cleaning them. From that same data set we mentioned, I think we ended up having about 900,000 yield data points across the 10 years, and we ended up getting rid of about 20% of them because it was just nonsense. Not enough nonsense. When you're in the pressure of harvest, you've always got 2 or 3 swaths that aren't full, so you need to get rid of them, and you're turning on the headlands a couple of times, so we do have to get rid of them before we start to really have confidence in the actual value. And if that's what we need to recognize that. If that's not what we're interested in, then great, just look at them and make informed interpretations from the spatial variation alone is fine. But if you're using them for more informed decisions, do certainly use the tools available.
One of the ones you mentioned earlier, and I've been sort of interested in this for a little while, it's something that's been available in the forage sector for a bit longer than the grain sector, which is NIR, near infrared spectrum, which looking at then grain characteristics as it's been done with forage on, so some, John Deere's Harvest Lab would be an example of it, and being done for slurry as well when a spreading, so you could control nutrient content being applied to land. But it strikes me a bit with that with yield maps, you're getting sort of one, particularly if you want to look at something like nitrogen, you're getting one dimension of a result. There's another dimension in the result, which is obviously the protein content of grain. So you've started to look a little bit at some of these NIR systems and data. What have you learned from it so far?
I suppose to start the fundamentals, we know grain nitrogen, grain protein has a strong indication of nitrogen uptake, and we're actually looking at N response trials. We know that generally there can be an optimum grain N and an optimum grain protein for economic N optimum. So we can use it as a way of identifying whether we're closer or further away to our economic N optimum. And it also allows us to calculate nitrogen use efficient. We can calculate how much N is taken off with yield, and that's what we do in our plot experiments. Now, the NIR sensors work similar in the sense of a yield map. As they're fitted to the combine, as the grain comes through into the combine, it will give you a measure of grain protein or grain nitrogen. So with that yield data, we could start to create spatial maps of nitrogen use efficiency, which will be really, really useful. Particularly, we have benchmarks, RB209 suggests for feed wheat that 11% grain protein is optimum for yield. So if we have an area that's consistently 12-13% grain protein in feed wheat, we can suggest, well, look, probably economic N is, we're putting too much N on there. We can make those decisions. That being said, as you mentioned, that it's not widely used currently. I think John Deere have about 20 these Harvest Lab systems in play, and there's some you can get them retrofit to other combines. And at Morley we have done that. We've got one retrofit to a class combine, and we're validating it under the technology is reasonably well validated in the literature and on experimental sites. What we want to know, like the yield maps, is how well do they perform when you've got 800 hectares to combine in 1 month in August and you only have 6 days of dry weather.
And you've got it sitting on a machine that is inherently not a laboratory environment.
Yeah.
I mean, the concept of NIR has been the standard for grain measurement. Yes. It's and I guess for people listening perhaps aren't familiar, it's a prediction of grain quality, isn't it? Because which is a key point. It's not actually it's not an analysis of grain. It's sort of a prediction of it. But every grain sample that goes into a lab, it's an NIR piece of equipment, the FOSS or the Perton equipment that's used in grain labs. So there's the science behind this is not particularly unusual or in many ways innovative. It's the placing of it to create real-time data within spots in field. But to me, it has quite a few interesting potential. One is to understand, as you just mentioned, nutrient use efficiency or nitrogen. Well, because it might not be just nitrogen that you could sense with it, but also to be able to, if you're a milling wheat grower or malting barley grower, that you can know very, very quickly where you should be sending trailer loads of grain off the field, whether they've made spec, whether they should go into a shed for a high grade product, or whether they need to go in a feed heap or somewhere in between the two. And actually that could be, from a market point of view, also really valuable. But we might also learn from that things that we need to do to make crop quality more consistent for end uses. So more consistent grain proteins for wheat, more consistent barley nitrogens, or as it's two sides of the same coin, protein and nitrogen, but obviously we talk in different terms of the crops, but which might have a value in the supply chain as well. So these technologies, it's more than necessarily just refining our use of the input. It could also be improving our crops.
Yes, and likewise, they're not as these new precision ag technologies, effectively what they are, come online and on stream, for want of a better word, and onto farms. They're not necessarily replacing older or current technologies. They're actually probably just improving and getting more value out of the other technologies we already use. We've mentioned the N sensor. You can apply based on the N sensor currently, and you can look at your yield maps, and we've discussed the limitations of trying to even a field out. But when we have grain nitrogen content across that same spatial area, well, that's another piece of information to validate what we're doing with the N sensor, or however we are making more informed nitrogen management decisions. So it's improving our understanding of other technologies as well as a new technology. And I suppose, you mentioned electroconductivity's been around for a long time. We've got other soil proximal sensing technologies around currently. Gamma ray spectrometry is coming on available, and even LiDAR elevation data that EA have produced, those sort of things, and well, actually together they can perform a much bigger, or give us much more information than on their own. EC works to quite a deep, we're picking up differences in subsoil, which we can't do a lot about, whereas Gamma tends to work in the top 30 centimeters. So those two together might say, well, this is variation in a topsoil, this is variation in subsoil. Now, again, we're fundamentally only really measuring one or two things from those. So we then have to go and do some ground truthing with soil sampling. Nothing's probably ever going to replace getting out there with a spade or an auger and figuring out what those differences are that we're picking up from these proximal sensors. That is the fundamental point. I think because those sort of precision ag technologies aren't getting us to inform what a specific level is. It's just telling us where we best to sample to get our accurate measurement. But those two together are much more valuable than one or the other on its own. And as we've discussed, yield mapping, N sensor maps, and grain protein all together provide a much, much bigger picture than any of those technologies on their own.
I'm going to ask, this is probably a slightly woolly question, or this is probably not the simplest question to answer. One of the great things about making future predictions is, luckily, by the time if you set the timescale far enough out, then by the time we get there, nobody will quite remember what you said. So if I say to you then, where do you think we'll be in 5 years' time? But I'm sure we won't hold you to it. How do you think these technologies will be transforming what we do in 5 years' time?
5 years isn't that long.
You can go for 10 if you'd prefer.
Yeah, I suppose it's probably worth looking back. In the last 5 years, I've only been in the industry sort of, actually on the industry, apart from outside of it, for 5 or 6 years, and I've seen a change from how these, certainly the software that's available for farmers to look at all these data sets together, that has progressed considerably over the last 5 years. And we've got various different companies pulling out their own probably all doing very similar things, but really useful ways of integrating those data sets. Now, I would like to see the next 5 years of farms and researchers to then say, right, we've got these data sets together, we can use AI, we can use machine learning, we can use targeted soil sampling. Let's spend the next 5 years getting to a point to really understand how these data sets together can provide value. So I would like to see more testing of those, the technologies that we have. And I know, Will, you were involved in a NIAB survey looking at members, and
Yeah.
I think 65% of yield farmers were yield mapping, or 50% were using variable rate. I can't remember, 50%,
I
I
can't do
believe.
that figures, but yeah, it was very high proportions. But there was some quite interesting things in there. There was a number of people who were doing variable rate crop protection.
Yeah,
It's really difficult to do.
yeah.
At the moment, but it's something that's very desirable.
Yeah, and potentially something as us as researchers are maybe not doing as much. Bearing in mind that 50% of people we work with are using variable rate technologies. Is it represented enough in what we do on farm in our research? Maybe not. So actually, I'd like to see a bit more ground truthing of these technologies as they come along, and really evidencing that they are helping us deliver economic. Now, we know with SFI and pressures on net zero coming in, I think the next 5 years will also see us go from using these technologies purely an economic point of view to saying how can they be used to arrive at environmental optimal management strategies. Actually, this is the economic optimum, this is the environmental optimum. You can then make informed decisions on where you want to fit within those two.
And they might not on some things actually end up being that far apart either.
No.
If we're using inputs really, really well, if we can drive efficiency of the use of inputs and reduce, then that should be a net improvement to the environment of not losing these things to water and leaching, etc. So, one of the things I've always been a bit concerned about with precision technologies is sometimes that they enable us to do things without knowing why we're doing them. And so, for example, we've been able to vary rates of inputs since, I think, the first example I can think of would have been Massey Ferguson's Field Star system in about 1995, 96. Anybody who knows how old I am will know that there is no reason why I should be aware of that at all, and I should have been doing much more interesting things at what the age I was at that point. But anyway, we've had a lot of things we've been able to do for a long time, but I'm not sure we've necessarily known why we're doing them, or we often might be thinking, well, we must be doing the right thing, but not actually being able to verify that. The thing that seems to have changed for me now is that we've got the capacity now and more of the technology to allow us to actually work out whether we're doing the right thing or not. And do you think that's a fair assessment of where we are versus, say, where we were 10, 20 years ago with these things?
Definitely. And I think we've certainly got probably more understanding on what the right thing is as well. We only have to look at the sort of interest soil health has got over the last 10 years and how we can measure that. We can measure it biologically with various different lab tests, but counting earthworms, or look at the AHDB scorecard. That, although those measures were there, they've now been put into a nice handy way that farmers can go out and measure their soil health. Now, over the next 5-10 years, hopefully, now we've got those sort of better understanding on how we can measure those things, we can use these PA technologies to go and then inform us and do those AHDB scorecards on various different areas of the farm. Whereas when we didn't have one or the other, together there. So yeah, hopefully these systems over the next 5 years will allow us bring in our understanding on soil and crop productivity, and will help us understand that and then help us implement other technologies you mentioned. Can we improve the efficiency of them through those technologies? And the work is certainly accelerating exponentially when we look at robotics and precision spraying and things like that. So yes, I think it will move quickly, and it will move much quicker than it has done in the last 10 years, as we have not just technologies but software and AI and machine learning particularly, that will help us interpret these data sets we've been collecting.
David, that's been brilliant. I've really enjoyed having this conversation. I know we could carry on for some time, but
yes,
we probably ought to draw to a close. Maybe there are some bits we should have a sequel on. There's obviously one big topic with data, which is about value and security of data we haven't talked about as well here, which is perhaps a topic for another time and would be an important one.
Yeah.
those listening, thank you very much for listening through, for joining us. We do have some more podcasts planned at the moment. We will be talking about, we've got integrated crop protection and with Aoife O'Driscoll, our disease expert within NIAB. We have a podcast planned with Elizabeth Stockdale, so she's been chairing a number of them, talking to people about carbon. It's going to have the tables turned, and I'll do an interview with her talking about regenerative agriculture fairly soon as well. So a little bit of variation in the different sort of topics we're covering, and as ever, we look forward to welcoming you to the next podcast. Thank you very much for listening, and thank you, David, for joining us.
Thank you.